as well mentioned, I work as a data scientist at Nvidia. So Pinterest, Netflix, Snap, if you've used any of these apps before and you've experienced an AI-enabled feature, maybe a voice recognition software or a recommendation engine, there is there are a lot of chances that that software or that model, machine learning or deep learning model, is probably running on a GPU. And you're now meeting a person who has helped make that happen. Hi, everyone. My name is Akshat Arora. I'm a data scientist at NVIDIA. And as part of my job, I work with NVIDIA's partners and help them optimize their machine learning and deep learning pipelines. So today, we will be pulling from those experiences, and I'll share with you a specific use case of machine learning and how do we enable GPUs on it using a specific library called RAPIDS. So that's me, and let's move forward. All right. So if you haven't been living under a rock for these past few years and you're working in computer science, you probably know what machine learning is. So just a brief introduction, machine learning is a set of algorithms that allow a machine to learn by itself without being explicitly programmed. Broadly speaking, there are two different types of machine learning. One is called supervised learning, where in the model, I give it the questions and the answers. The model figures out the patterns that exist between those questions and answers and is able to learn those patterns. Now, as this moves forwards, we have a trained model, we can then deploy it in a real system or a real use case, and given an unknown sample or given an unknown question, it can detect and give a classification or give an answer to it. The other type of machine learning model is called unsupervised learning, where in this case, I don't give it any answers at all. So I only present it with a data set. The model figures out a way to find patterns in the data set itself and figures out which clusters exist. So that in this example, as you can see, it figures out how three of these cartoon characters look the same. That is a duck, right? And it identifies these patterns, and they can be useful in all sorts of applications. Moving forward, why is machine learning important? Like, why is it important to accelerate it? So this is a tweet from Francois Cholat, where he talks about how do people win Kaggle competitions, right? Before we move forward, can you please verify that you can see the zoomed in version of my slide that I just did? Bill?
Yes, we can see that.
Awesome. All right. Just wanted to make sure it works before I go on and zoom out. Thank you so much. So this is a tweet from Francois Cholat where he talks about, winners are those who went through more iterations of the loop of progress, going from an idea to its implementation and then to actionable results. So the winning teams are simply those who are able to run this loop faster. So he talks about this loop, right? What is this loop anyway? And in terms of machine learning, and but what does he mean by accelerating this loop? You're all familiar with Kaggle, right? It's a data science competition. And how is this accelerating machine learning a recipe for winning these competitions? So this is the loop that he's talking about. Once you have your data set from any domain, for the first step that you do is something called data preparation. So you do some ETL logic on top of it, extract, transform, load. And then after that, you train your model using that data set. At the time, you might want to perform some visualization or hyperparameter tuning to make sure that your model is the right model to go out there in the real use case. And then you deploy your model. Now, the reason it says it's a loop is because as soon as you deploy your model, it's already out of date because data is coming in from the real world all the time. So you can't just like train your model on the data set and then expect it to be the current model at all times. So all you need to do is when you deploy your model, you look at certain metrics. Maybe you look at throughput, latency, accuracy, and then you determine whether you need to change your model. And when you decide to do that, you go ahead and go back to the data preparation stage, do the model training again, and then deploy it again. So this is the loop that Francois was talking about, and this is what we call a machine learning life cycle. This will be the overview of my talk today. We will start by talking about a specific machine learning algorithm called random forests, and we'll talk about how it's trained and then how GPU, which is something known for its parallelism, leverages that algorithm and then accelerates it. And then we'll talk about, we'll zoom out in this life cycle and we talk about data preparation and model deployment and hyperparameter tuning. Um, and then we'll talk about how, RAPIDS came out of all of these learnings, right? So let's move forward and let's talk about random forest, right? So what's the intuition behind random forest? So the basic building block of a random forest is a decision tree. This is a small subset of that decision tree where you can see there are certain number of samples right here. And based on a feature X, based on if it's less than 2 or if it's greater than equal to 2, you can classify that sample into blue and green. We'll talk about how this matters in the larger context of random forest, but this is a very basic building block. This is what it looks like. We'll come back to it later. Idea is to have these small decision trees all the way and have each of them exist independently. And what we want to do is whenever an unknown sample comes in, we would like to then classify or make a decision out of each such tree. Like for this example, this tree makes a decision that the unknown sample is blue. And we have 3 blue decisions and 1 green and 1 red. So in the end, all you need to do is take a vote. And blue, basic idea behind random forest, you have these randomized, we'll talk about decision trees. Each of them makes a decision on an unknown sample and then takes a vote on what the unknown sample represents. In this case, let's talk about it in an example of a toy data set, a fruit data set. And when I say features, I mean, as you can see, we have red, green, blue, and size. Instance is just like a primary key to this table where it just represents each row as it's a unique identifier in the instance column. You have red, green, blue, and size. They are your features. They are what represent a sample. And then you have a label column here, right? Now, since I'm giving it label as well, since the label column exists, that's the reason we say that it is a supervised learning algorithm as discussed before, because I'm telling it the question and I'm giving it the answer, right? So first step to making these random forests out of something like this existing data set with replacement. And when I say with replacement, I mean, sorry about that. So when I say with replacement, I mean, take a look at the subsample data set. I took 3 subsamples, and this is the first, this is the second, and here is third. Now, you might have noticed that at some point, there are some instances that exist in more than one with ripples. How do we derive of each of these subsamples? So we need to look at an algorithm that can guide us on how do we build a decision tree out of a subsample of this data set, right? So now what you need to do is read all of these textbook algorithm, or I can just guide you in the right direction. We can skip this part. Is you need to make sure that whenever you're building a decision tree, you're going towards more and more purity in the data set. So think of it this way. When you start your decision tree, right, when you have that small subsample of data set, it probably contains cherry, strawberry, and bunch of more categories, right? So it's something that we call very impure group. But as we go down and as we split the tree into two different parts and then go down a decision tree, when we're building a decision tree, we want to make it more and more pure or less impure. We want to achieve what we call minimum impurity. And the way we measure that is called Gini impurity. It's a mathematical expression that you can calculate and figure out which feature do I choose such that the entire decision tree goes to more and more purity, right? And you can look at it when we talked about, here, if you think about it, at this point, we have both blue and green samples. We figured out that X is that one X is that one feature based on which if we split, it will lead to blues getting gathered on the one side of the node and greens on the other side. So the idea is to identify, okay, given the subsample of the data set, what is the feature that I should split on? And then the second part is, what is the feature value that I should split on, right? There are many ways to determine like the feature value. We won't go into detail there, but it is of relevance in this conversation, and we'll see how. So far, we have these subsample data sets. What do we do now? We understand how to make the decision tree out of a single data set. So what's the result here, right? So for the result, we have these three decision trees out of each of those subsample data set. Now let's examine one of these and see what it says, right? So in decision tree one, as you can see, the first question, as we were training it, the first question it asks, it figured out if I ask about size, it will make a lot of difference. So it says, if the size is greater than 3.9, then it's definitely an apple. If the size is less than 3.9, it figures out that I should ask another question, which is, what is the size relative to zero point 0.9? If it's less than zero point 0.9, then it's probably a cherry. And if it's more than zero point 0.9, but at the same time less than 3.9, it's likely a strawberry. So do you understand how easy this model is to interpret? This came out of a single decision tree. We have multiple of these because we were able to decide, we were able to get different subsamples of our data set. So this is how, there you have it. This is the random forest model of the data set that we saw earlier, right? Now, if you think about it, how do you implement this on scikit-learn? So as you might have already been aware, you have these standard import statements in Python. You go about and you have these parameters that you need to specify in scikit-learn for random forest. Now, the first one is number of estimators. By number of estimators, I mean that you need to tell how many trees or how many estimators. If you think about it, each of these three trees are in themselves estimators, right? How many estimators should you have? How many trees should you have? And then after that, it talks about max depth. With each tree, what is the maximum depth that you can go for? Now, why is this a parameter that we need to specify? So think of it this way: more the depth of your tree, the more compute it will take at runtime or at the inference time of the model to go and spit out a value or a result, right? So ideally, you want to minimize your max depth and get as many best results as possible, right? And then you have n jobs, which is basically saying how many parallel jobs do you want to run on CPUs. And at this point, we imported multiprocessing and we have a method called CPU count that gives you all the 40 cores or whatever number of cores you have on your CPU to this job. After that, you need to instantiate a scikit-learn random forest instance, and then you call a fit method, which then takes X train and Y train each row of X train is basically a row containing features of that sample. And then each row of Y train corresponds to the row in X train that says what is the label of this. So as you can see, when we call fit function, we give it both questions as X train and answers as Y train. Now the next step here is to call a predict function on X test. As you can see, X test is a list of unknown samples that we want to make predictions out of, right? Now at this point, X test will have all these features that you want to get a result out of. And then you can print out an accuracy score based on what did you predict for that particular X test and what were the real answers, which is represented as Y test here, right? This is a typical sklearn implementation. Now, to talk about it, so far we have gone through random forests and how it's trained and what's the intuition behind it. But what were the acceleration opportunities in there? Like, did you notice, is there any way that GPUs, which are so great at graphics and parallelizing stuff, how can we leverage that parallelism on random forest? So if you think about it, the first thing that comes to mind is all the trees were independent. So while developing each tree, you don't really care about the other trees, right? It's completely independent compute, and that can be parallelized using GPUs. The other thing you want to notice is that when in sklearn implementation, you usually have depth first development of a tree. So what you do is basically just like depth first search, you go each depth one at a time and figure out what the split should be and then go again, right? But in GPUs, what you can do is do a breadth first search, because if you think about it, right here, all of these trees, like once I figure out that the size greater than 3.9 is Apple, or if it was another feature, the left side of the parent node and the right side of this parent node are completely independent of each other. They've already divided the task. So if I can parallelize using breadth first search, I can get a lot more acceleration while training this algorithm, right? So that is the second point. We use breadth first search. And then the third point is when we have high performance split algorithms. So remember when we talked about to determine where to split, you need something called the feature, which feature to split on, and then what is the feature value that you want to split on, right? So in order to determine the feature value, you have some split algorithms that you can follow, and we won't go into the details here. One is quantile, and there is min max. But if you can have those particular algorithms, accelerate them with GPUs, you can really get fast at exploring each feature plus node combination, right? That exhaustive search of where to split can become really fast. So those are the three acceleration opportunities that GPUs can leverage, right? And you might wonder, like, you were getting all of this, what do you need to do in order to make it work? Well, it's very simple. It's exactly the same as you had to do it in scikit-learn. All you need to do is just change the import statement and use QML instead of scikit-learn to instantiate your random forest classifier. So in this case, we make that slight adjustment and the rest of the code is the same. You define the same parameters, you instantiate a QML random forest classifier, you give it the same parameters, you call a fit function, and then you predict the values and you calculate an accuracy score. It looks exactly, the API definition is exactly the same, right? So how do we then, what is RAPIDS, right? Let's talk about RAPIDS now. And now that we know how do we train in scikit-learn and how easy it is to port a code that goes from scikit-learn into QML, which is Rapids QML, and so easy to port it is, right? Now, moving on, is it effective? Is that acceleration, the points that we mentioned, are they effective at all? So we ran a little experiment where we compared QML, with scikit-learn on a DGX1 server, which is NVIDIA's 8 GPU card. We have B100s, very powerful GPUs with 16 GB. Although we are using only a single GPU in this experiment, um, the DGX1 server is configured with 8 GPUs. And then we have a dual Xeon E5 CPU with 40 cores. Um, we did this experiment on 28 columns and 11 million rows in something called a Higgs data set. It's a pretty standard data set used for benchmarks. And here are the results, right? So if you think about it, all these little bars, each bar is actually number of trees and max depth. If you remember from the code that we just studied, those two are hyperparameters. So we can change those and as you can see across each of these speed up bars, you get at least 20x to almost 45x improvement over a Higgs data set. And if you notice, the bar axis here is speed up. They're all factor speed ups from QML and scikit-learn. And QML consistently performs better on each number of trees and max depth combination. And then you have these little line bars over here. What do they represent? They are accuracy. If you think about it, the blue line that you can see behind the red line is QML accuracy. And then scikit-learn accuracy is the red line, right? And as you can see, they are almost superimposed. And that's the powerful RAPIDS library giving you the same accuracy with so much speed up on 11 million rows of data set. And now you can say, hey, maybe it's only the Higgs data set that works well with QML for some reason. We also repeated our experiments with synthetic data sets, the exact same configurations on the hardware level, and we got nearly 25 to 60x speedups with the same accuracy. And that's something, right? Like that's something to account for. If you could port your code that looks the same, except the import statement to GPUs, and you're getting so much speed up. Now, this speed up actually accounts for business value. How? Think of it this way. What if, like, as you know, Francois mentioned that you can win Kaggle competitions, but beyond that, if you are, as you deploy a model, as I said, it already goes outdated, right? So the recipe to make it updated pretty soon in production is to update and train your model every hour or nightly, or as soon as possible, as soon as you can, so that your website or your web service is always up to date and goes on with the trends, right? It's important business value that you can't afford to miss out on. And that's where Rapids really shines, right? This is something that you can run repeatedly on your servers and get the same accuracy with so much speed up, right? So let's talk about what are some of the core ideas behind Rapids. Now, if you think about it, about 10 years ago, this is how our data pipelines looked like. You had HDFS, Hadoop processing, you were reading from the disk. For every single thing, for query, ETL, and even machine learning training, you had to do two necessary steps, which is HDFS read and HDFS write. You had to read from the disk, do your compute, and write into the disk, and so on. You had to do it over and over again, and this was a huge bottleneck about 10 years ago. Then came in the Spark in-memory processing, where everything was done inside memory. So you only have to read it once, and everything else is done inside the memory. You have query, ETL, and ML training model with fairly less code and a good amount of flexible language. And primarily everything is done in memory. And then came along GPUs, right? You got about 5 to 10x improvement over GPUs. And the way you would do that is you would read from HDFS, you would read it into GPUs, you would query, you would write it back to CPU, you would do ETLs, you would have to write it back to CPU, right? And if you think about it, like these CPU writes are a problem. How? Let's talk about that. So let's say you have two applications, right? Application A and application B, they are trying to communicate with each other. and both of them have their data sets on GPUs, right? So if you want to transfer, let's say, a data set from application A to application B, of course, both of the applications understand different formats. So you would have to go to, first your GPU data resides in the GPU for application A. You go to CPU, you copy and convert your data set in a way that makes sense for application B, right? And then application B, what it does internally is copy it right back to GPUs. So what if we could get rid of these extra copy and converts, right? Wouldn't that be something? So that's exactly where another big contribution from the big data community that inspired Rapids a lot was around Apache Arrow. The idea was that existing big data libraries, they have to do these copy and converts to talk to each other, right? All the time, because each of these libraries have their own data standards. There is no common data standard that every one of them adheres to. And hence, we shifted it and we introduced this idea of Arrow, Apache Arrow memory, where everyone can just adhere to a single format. And once you have that, every single library can then just needs to pass the pointers to the data set instead of having to do actually copy and converge over and over again. This saved a lot of time in just doing these redundant data copy and converts, right? And this resulted in what we call rapids today. So you get about 50 to 100x improvement where you just need to perform an arrow read from the GPU itself, do the query, ETL, ML train at the GPU itself. You don't need to interact with CPU anymore. And that is the core idea behind Rapids, right? With very minimal code change, you can achieve all of this. And that's a huge, huge plus for me, at least. If you think about the open source data science ecosystem today, it's you must be familiar with these Python APIs. You have pandas for analytics to do the ETL of the data set. You read in the data set, you perform some sort of data preparation, as you mentioned before. You have scikit-learn for machine learning, for running any machine learning workloads. You have network X for graph analytics. You have PyTorch, TensorFlow, MXNet for deep learning, and then you have Matplotlib for visualization. All of them currently use CPU memory. You also have something called Task, which is made to extend the capabilities of pandas and scikit-learn. And we'll come back to that in a second. Here is what Rapids vision looks like, what Rapids library today looks like. This diagram needs to be updated. We do a lot more than this. But this is what Rapids looks like, right? You have KUDF, or if you can allow me to say, CUDA accelerated data frames, which is pandas equivalent, but it's in terms of like we try to mimic pandas in as much as we can in terms of API definitions because it's very intuitive. And then we add GPU acceleration on top of it. And the same is true for QML, CUDA accelerated machine learning. We do the same thing with QML for scikit-learn, where the API definitions look the same, but you have all of this like acceleration opportunities within all these machine learning algorithms that we implement behind the scenes, and you're able to access them using QML. With cuGraph, we do the same thing with Network X. It's GPU accelerated graph analytics. With deep learning, we still use PyTorch, TensorFlow, and MXNet. We have strong interoperation libraries that you can use to take a data frame from KUDF into PyTorch, KUDF into TensorFlow, and that's pretty cool. We have cuCrossFilter, PyViz, and Plotly for visualization. Now, they're all interacting with GPU memory, specifically speaking, they're all interacting in Apache Arrow format. So you can use all of these libraries interchangeably, and like you can transfer data sets to each other uh, as easy as possible. And on top of that, we also have Dask, which is accelerating and taking one step further the capability of QDF, QML, QGraph from a single GPU to multi-node, multi-GPU, right? and even single node multi GPU configuration. So we extended DAS to work with GPUs, and we will talk about how do we use that in our example in a second. And yeah, this is what Rapid's end-to-end GPU accelerated data science looks like today. So moving on, let's zoom out, as I said, and let's talk about KUDF, right? What are we doing with regards to how does it look like to use KUDF and how beneficial is KUDF, right? Uh, CUDA accelerated data frames. So first we have import statements. You read the data set. For folks who use pandas can recognize this method called read CSV. You read in the data set, you divide the data set into train and test, where training is about 80% of the data set and testing is about the remaining 20%. You have the same parameters, same fit function, predict, and you can get the accuracy score. The remaining part of it we've already discussed when we were talking about QML implementation. So really, it's that easy, and it looks really similar to KUDF itself. Now, is it beneficial, right? Let's talk about if it's beneficial or not. So if you think about it, we have this data set, yellow trip data, which is about 2 gigs, right? On a GPU, on a CPU, you take about 30 seconds to read this data set. On a GPU instead, you take only 2 seconds. Now, right now, you're saying it's only 2 gigs, and now there are hundreds of gigs or even terabytes of data set. It all scales pretty well, right? As you can see in the small benchmarks that we did, uh, you have the violet as 10 million, and then the blue is 100 million. The speed up over of GPU over CPU increases as you go above and beyond when you're in your data set, right? And that's pretty cool. I would say for each and every of these merge, sort, group by, which are the most commonly used Python or pandas operations, to get these speedups incrementally in an incremental manner is pretty great, right? And all of this adds up when you go even bigger data sets. So that's how QDF is beneficial and can accelerate your machine learning pipeline. So moving further along, we have Dask QML implementation. Now, in this case, we'll be talking about how do you take random forest. The previous implementations work great on a single GPU, but how do you take it like multi-GPU or even multi-node multi-GPU, right? This is how you would want to do it. You import Dask and the necessary libraries within Dask. You instantiate a local CUDA cluster. This is specifically for when you want to do single node multi GPU configuration. The code varies slightly when you want to go to multi-node. Um, you define data parameters, how much train, how much test size. You define what is the hyperparameters for your random forest. You generate a data set. This is a classic example of generating a data set. As most of you are familiar with scikit-learn, this is what you would do. You would use make classification to build out a sample data set. And then moving forward, you have how do you convert your QDF uh, data frame to Dask data frame, and then persist that in an active memory. You basically are loading your data set onto the memory, and then all you need to do is just call fit function and wait for the training to complete. So that's how easy it is to have Dask QML application basically accelerate your your training, model training. Now, today, the important thing to note about multi-node, multi-GPU capability is that you can scale it out to virtually any amount of data sets, so long as you have the necessary nodes on AWS or GCP or even your own on-prem services. You can basically scale it out to a lot of different nodes. And today, we only support these particular algorithms as multi-node, multi-GPU. Soon more support will be added. We are still Rapids 0.14, and this is our road to 1.0, right? And just excited to see where you guys use all of these models. All right, and moving forward, we also have forest inference library. So remember, we talked about data preparation. We talked about scaling the data preparation and the model training to multi-node, multi-GPU. And now we're talking about how do you inference, how do you make inference, right? So here you have Forest Inference Library, which currently support XGBoost like GBM models. All you need to do is import the library, load the file that has the model in it, and then just call predict. Is this simple thing effective? Pretty much. We ran an experiment where we had all of these data sets. Higgs, you're already aware. We had Bosch, Airline, and Epsilon. And you got about 23 to 36x speedups. And all of this really makes a difference in production and really drives a lot of business values. This is when you have 1,000 trees, XGBoost, the CPU time has been captured on 40 cores, and GPU time has been captured on a single V100 machine. And these are the speedups that you get. It really tells you about how Phil or Forest Inference Library is driving business value. Um, did I say we were done? We're not. There is actually one more feature that you all should be aware about. So hyperparameter optimization. This is something we recently introduced at Rapids. And the first and foremost thing, we work with our cloud partners, which is in this case Google, Microsoft, and Amazon, for Google AI platform, Azure ML, and SageMaker respectively, and we enable data scientists to go ahead and run their experiments on all of these nodes that they have available. Right? Usually, companies are in a contract with one of these cloud providers, and they have the access to all of these nodes. How do you use them to run multiple experiments and do the hyperparameter optimization in parallel on all of these nodes, right? An example of doing this would be if you're running an experiment on your own machine, you would have to run it all in parallel, right? You have experiments 1 through n, you're running all of them in parallel here. Now, if you have access to a cluster, you could run all of these experiments using, all the power that Rapids is giving you in parallel on a cluster, all the different models that you want to try. And this comes back to the point that Francois made, right? The faster you go through this loop, the faster your chances are to drive real business value to your company and to whatever it is that you're doing, if it's winning a Kaggle competition, right? And basic workflow, it's an example of how to use it on SageMaker, which is Amazon's classic way of tracking machine learning and deep learning workloads, is you build a SageMaker container. For those of you who are familiar with how to build like custom containers, you need to customize the Rapids container, and you need to push in your train script right there. You need to push that to a container registry that exists within Amazon, and you need to then enable SageMaker to access that and run all of these experiments in parallel, and in turn communicate with S3, which is a bucket or a storage solution by AWS, uh, and where all your results will be stored. SageMaker also gives you an interactive way to look at your experiments and the results and a nice GUI, and you can check it out on SageMaker's website. Um, is this effective? As I said, you drive a lot of business value when you do this, right? So this is, again, an experiment that we ran. As you can see, Rapids takes literally less amount of time and less money. And what can be more beautiful than that, right? But given the current GPU nodes pricing and the CPU nodes pricing, there is real business value to be captured when you're running it on, in this case, we measured this on Azure ML. Uh, so there's really something that you can leverage here, use, right? All right, moving on. So today we learned how do you go about accelerating machine learning pipelines, right? So all of you right now are aware, fully aware, somewhat aware of this ecosystem where you have Numba, scikit-learn, pandas. You have single CPU core, in-memory data. Now, if you want to accelerate it by taking it to multi-nodes, you can do it using Task. So it works with NumPy, pandas, scikit-learn. and everything else, right? You can use it with task. Or if you want to make your current node more powerful by adding GPUs to it, you can go ahead and use Rapids without any code change. So all you need to do is change the import statement, and the entire code base will run as is. And that's what Rapids' vision is. That if you add GPUs to it, you should use Rapids. Right now, moving on, if you want to do GPUs as well as multi-node, multi-GPU configuration, the ideal way to do that is use Rapids, use something we call OpenUCX. We didn't get the time to talk about it today, but it is just a library that accelerates the interconnectivity or the messaging between GPUs. And then you have task, right? You can use all of these three things, and you can go as many as wherever you want, right? You can scale out and scale up, and that's what the ecosystem looks like when you want to accelerate it using GPUs, right? And that is what we recommend. So today we didn't get to talk about a lot of different libraries like QSpatial, QGraph, and I would love to talk to you guys about it sometime. But this is where we are. I think we're at the top of the hour, and thank you for joining. You can use this link to get presentation. Let me, okay, how do I exit this? All right. You can use this link to get to the presentation that's on my GitHub. And I have some suggested reading that you can go through and read about all the things that we've discussed today. And then you can also go to Rapids AI homepage and get started. Really, I can't wait to see you guys king the tires. All right. Thank you.
Yeah, that's great. You probably also can copy paste the link, post it to the chat, so it's
Sure.
probably easier for the attendees to get it. And then we are on the Q&A sessions. Let's can you open up the Q&A and we can go through the questions. I see quite a lot.
Awesome. I can post to the chat here, right? All the panelists and attendees. Right.
Yes.
So here is the link to
Okay.
the Git
Yeah.
repository.
Perfect.
Yeah. Awesome. All right. So the questions, I have quite a few. Open. Okay. So we have single likes on each. All right. At each split point, do you consider every single available feature, or do you pick a random sample of features and try to do the best using a subsample of features? Yes, that is correct. As Mohammed says that, there is something called feature subsampling that you do at this point, where that is the reason why this is called random forests, actually. At each point, you have the subsample data set, and you need to choose either, randomly choose any sum of the features right here where you want to split. And that's really what drives, the fact that all of these decision trees are different. The reason behind that is also this feature subsampling is randomized, and hence all of these decision trees look really different. All right. I'm a good fan of NVIDIA products. I'm in the process of using Rapids, but I was hurted by technical issues behind getting it installed. Who can we get in touch with in the community to get support in future? So Rapids is an open source library, right? If you want to get started, it's as easy as going to get started here, and right here, when you can use Conda, Docker. Even if you are an expert, you can use source, or you can compile it from source. What I would recommend is to use Docker to get started as soon as possible. So if you have a GPU instance, this is where you can select, okay, you want to work with 0.14, which is the latest stable release. You can have all the packages. You can choose which OS version you want to run on, and you can choose what Python version you have, right? So based on that, you can drive that answer and how to all you need is this command. You can copy and run it right there. So I hope that answers your question. All right, there's a new question. How is Rapids integration with Spark, mainly for Java, Scala APIs? So I'm gonna go ahead and post another link, uh, which is Rapids Spark notebooks, actually, Spark examples. So if you go to here, by the way, Rapids team maintains this page with all the libraries. As you can see, we have KUDF, QGraph, QSignal. We didn't get to talk about QML. But just to answer the question, we also have something called Spark examples. We seem to be stuck here. All right. Okay. Spark examples. If you go here, you'll find examples of both Python and Scala, and I urge you to try it out. The collaboration between Spark and Rapids is still developing itself. We recently released an integration, and I hope you can try it out right here. So I can post that on here. All right. So we have that, and can I install it on both Kaggle and Google Colab? Where can be discrepancies in the environment at the time? So we'd love to hear about the resources. All right. So recently, one of the data scientists who directly works on Rapids, he does this installation on, I can send the link later, actually. I don't think I have it on me quite there yet. I think Chicago, yeah, okay, I have it. So this is an example of how do you use, and this is using k nearest neighbors. You get about 600 times speed up with using GPU on Rapids QML, right? This is the installation instruction that you can use. As you can see, it's an open source thing. A lot of data scientists at Rapids are actually Kaggle grandmasters. There's a lot to learn. So I urge you to go follow these scientists there and follow their work. They're pretty amazing. So I've posted the link to the Kaggle and how do you do it on Google Colab. So Google Colab would, I guess, be simple as installing on Rapids. Let's see. So we use Conda. You should be able to install it on Conda, or you can have it on Colab right here. We can pass on the link, but if you go to Rapids start, you can launch it on Colab. All right. Can I use these GPU-enabled libraries between environments with and without GPU access? So I'm not sure what between environments would mean in this context. If someone could clarify that maybe, or without GPU access, I don't think so. So here is the prerequisites that can help, right? You need Nvidia Pascal or better compute compatibility 6.0 plus, and we Google what this means. But basically, compute compatibility is something that comes with each and every GPU release. So you need to check what is the compute compatibility of the GPU that you have access to, and then go from there, right? We recommend NVIDIA Pascal or better. And there are certain prerequisites that you need to meet in order to install Rapids today. So I hope that answers your question. What is not get converted to GPU mode in the world of Python data science into the GPU-enabled libraries? So I assume you mean what is not yet converted to, what is not yet GPU accelerated, what kind of algorithms, right? There are plenty of algorithms that are very obscure and no one uses them, I guess. And those are some of the algorithms that we might have missed out on. But so far, if you want to see the support structure within Rapids for GPU acceleration, you can have a look at the, as I mentioned, the GPU library, the GPU, yeah, the GitHub page. And if you go to, let's say, QML, you will find a table that tells you the supported algorithms, right? So this is where you can find which libraries are supported. So I'm just gonna go ahead and Voice it here. All right. Getting these speedups is very nice, but what would be the average increase in cost? So it depends, right? It depends on the situation that you have. I'm sorry, these questions keep moving. Let's see. So what is the average increase in cost? So it really depends on, your agreements with the cloud provider, and also these pricings really change over time. I recommend using T4s. GCP like recently reduced the pricing for T4s, and pretty useful to get the acceleration on rapids. And also it also depends on, what are your business needs, right? How soon do you want to run? Can you afford to run, or what are the targets in terms of throughput latency that you're trying to achieve in the market itself? And that's what derives the cost, right? We've certainly done experiments on our side that show that there is savings in cost, as I showed in this slide here in the very end. When we do HPO, we have done similar experiments for other cloud providers as well. You can find it on some of the blogs that we have published. And yeah. What would be the average increase in costs? I guess we answered that. How about using Rapids and Jetson Nano? How can I compare it with a Volta or a high-end GPU? I'm gonna really have to get back to you on that, because I am yet to get my hands on the Jetson Nano myself, and get some fun with it. But I urge you to try it out. I believe we have some blogs indicating how to do that. But feel free to, as I said, email me. You can find my email right here, and I can get back to you on that. We certainly have some resources available on that side. Is Rapids available on other cloud providers like Oracle Cloud and other private cloud providers? As we said, you can always, compile Rapids from scratch, and Rapids is just a container, right? So you can, as long as the platform itself supports bring your own container, you can literally just go ahead, and all you need to do is either do a conda install or do a Docker pull and then Docker run. And there is no reason it shouldn't work, as it's an open source library, right? Anyone can adopt it, and anyone can make it work in their own environments. And we have, is there a generic script I can use to do the same thing you mentioned about hyperparameter optimization? Yes. So if you look at it, I'm just gonna go reduce my size of the window here so I don't interrupt Zoom. There is a library called Cloud ML that we released recently. So if you look at Cloud ML examples, here you will find scripts that you can adopt and customize to use in your own use case. But basically, we'll go through step by step how to do accelerated hyperparameter optimization on Microsoft, AWS, Google, and just gonna post this here, right? Awesome. So I believe we have some more questions here. Very good presentation. Can you share the slides with us? Yes. So as I mentioned, the slides are available here. As soon as you go to this GitHub repository, you can go ahead and click here, or please find the presentation here. You can get the slides right there. Here, there we go. All right. So I know we're already 3 minutes above our schedule. I'm happy to take all the questions on the email. Back to you.
I think we have a couple of more minutes. Let's probably take 1 or 2 questions if you can.
Sounds good. Yeah. All right.
Thank you.
I just wanted to check in with you, right? Because we had this conversation earlier.
Yeah.
Right.
We have another event coming up in 10 minutes. So.
Right. Okay. Please tell me more about Number plus Rapids. Is this out of the box or is it the same interface that Number provides? Number already provides GPU support. Yes, you can use Number to actually accelerate Rapids, and you can also use it to have user-defined functions within QML. I can, if you email me with your credentials, I can share that with you. I have a Number resource with me somewhere, and I'm just not able to pull it up on my screen right now because I've forgotten where I kept that. So you can reach out to me offline. I can provide that to you. Can we also use Java-like platform, independent language also? Now, I'm not sure I know the answer to that because if you think about it, Rapids, the layers within QML and QGraph, and for that matter, any library that Rapids runs, you will find a C++ layer that you can use to directly call those functions, right? There is that. I'm not sure how that would interface with Java, but I can find it out for you. I can ask around within the teams. All right, and we have, can we use it in AutoML or use it on AutoML platforms like AWS SageMaker, and also Keras and other deep learning frameworks. So for Keras and other deep learning frameworks, as I mentioned before, right, you can use, yeah, let's go there, right? Community, let's go to docs. We have an overview right here. So from this is where we keep our docs. You can view with each release, you know, what the new features are and a PDF associated with all the different features that we take care of. So if you go about it, we have, so we do interoperations between these libraries. Yeah. You can use DLPack and CUDA array interface to basically interact Rapids with all of these different libraries. And I hope this answers your question. We can have specific examples. I can share them offline, but this is what the support structure looks like today. And as far as AutoML or AWS SageMaker is concerned, I already mentioned in another question that you have these Cloud ML examples that you can follow step by step and use SageMaker in this matter and parallelize your hyperparameter optimization, right? So I hope this answers your question.
Great. And I think we have to stop here. And sorry about for the interruptions. I see we still have quite a lot of interesting questions here. I guess we can follow up with you on the questions offline with the emails.
Awesome. I hope everybody has received the links. And yeah,